So in that first one, you have two peaks.
Mm-hmm.
You have a 156 and a 158 for the M plus and M plus 2, right?
Mm-hmm.
So what's the molecule weigh?
158? Or what? Is it whichever one's taller?
No, it's 156 is the M plus.
Mm-hmm.
The M 156 or 158 is the M plus 2.
Mm-hmm.
And that's just for the isotopes of some element.
Oh, so
now,
it weighs 156.
156 is the main weight for the molecule. That's what you'd talk about in the M plus 2 being 2 higher. But what gives you an M plus to an M plus 2 of equal intensities?
Bromine.
Okay, so this has to have a bromine in it. What does bromine weigh?
79 or 81.
So we subtract out 79 or 81 for a bromine, depending on which isotope we're looking at. And what does that get us?
77.
Okay. Both of them are 77, right?
Mm-hmm.
So what can we subtract out of 77?
6 carbons.
What's that weigh?
72.
Okay. So that leaves us with 5 hydrogens.
Mm-hmm.
Can you give me an example of a compound that has 6 carbons and 5 hydrogens and one other thing? Do you know what that functional group is? Does that make sense to get an answer like that?
An aromatic ring, right?
Okay, a monosubstituted aromatic ring is C6H5, so you just have a bromine off of the aromatic ring, and that's your answer for that one. Normally you can't come up with the full answer just from the mass spec, but that one's easy enough that you can. What about the second one? What kind of functional group do you have in it with the weight being 156 and only the 2 fragments of 127 and 29? How can you explain the molecule weighs a lot, 156, but doesn't fragment much?
There's an iodine in it.
Okay, there's got to be something big in it. Iodine weighs 127. This 127 is from the iodine, but 127 doesn't always have to be from an iodine, so be careful about that when you're working problems. So the weight of the molecule is 156. Subtract out the iodine, 127. That gets us down to what?
29.
What can go into 29?
2 carbons.
So 24, 5 hydrogens. Can 2 carbons hold 5 hydrogens in an iodide? Does that make sense?
Mm-hmm.
How many things can you put on 2 carbons total?
If they're not connected to each other?
No, if just in a molecule containing 2 carbons, what can you do? How many hydrogens can you have on 2 carbons?
12. Right? No, 6.
Okay,
Apparently I can't think today.
double it and add 2,
Right.
right? So 2 carbons can hold 6 things.
I was looking at the 5.
We have 5 hydrogens in an iodide, which adds up to 6. So, yes, that works for the second one. So it's a good formula, C2H5I. The third compound weighs how much?
90. Or 92.
Okay, so why in the third one are the peaks in the 3-to-1 ratio?
Because there's a chlorine.
What does chlorine do? What does it have?
Isotopes.
What 2 isotopes do we have?
35 and 37.
Okay. When we subtract chlorine 35 from 90, what do we get?
55.
And when we subtract chlorine 37 from 92, what do we get?
55.
Okay. We always get the same thing when we subtract out from the 2 different isotopes. So we get 55. How many carbons go into 55?
4.
Okay, that's 48, 4 carbons. That leaves us 7 hydrogens. Can 4 carbons hold 7 hydrogens in a chlorine? That makes sense? How many total things can you have 4 carbons hold?
10.
Okay, 4 carbons can hold 10. We only have 8 here, so we have 1 unit of unsaturation that we talked about a long time ago, right? Remember that?
Kinda.
We're missing a pair of hydrogens from what the 4 carbons can hold total. We can't say anything about what we have about the whole molecule like we could in the first 2 because they were really easy, but we know the formula has to be C4H7Cl. Right?
So there's probably some double bonds in there.
There's going to have to be either a double bond or a ring in that molecule. Yes. What about the last one? What can you tell me about it?
There's nitrogen because it's odd.
Okay, the molecular weight is odd, 115, so we subtract out 14 for that, and we're at 101. How many carbons can go into 101?
8.
Okay, if we take 8 out, that gets us 8 carbons and 5 hydrogens.
Right.
Right? Does C8H5N make sense for what you know about organic? Or does something seem odd about it?
There's not enough, right?
Not enough what?
Molecules. Like, carbon would have lone pairs, right?
You don't have enough hydrogens for the number of carbons. Normally, you'll have more hydrogens than carbons unless you have an aromatic ring. So, in this one, the C8H5N doesn't have enough hydrogens for the number of carbons. So what we need to do is subtract 1 carbon, C7, and add 12 hydrogens. They weigh the same amount, 1 carbon, or 12 hydrogens. So 12 hydrogens and 5 gives us 17 hydrogens. So a formula for this one would be C7H17N. 7 carbons weighs 84, plus 17 gives us 101 for the hydrogens, plus our 14 for our nitrogen gives us the 115.
That's a whole lot of hydrogens.
But the formula works out for that in that C7H17N is a workable formula, right? If you just had 7 carbons, how many hydrogens could you hold?
16.
Okay. If you had 8 carbons, if the nitrogen wasn't a nitrogen but it was a carbon, how many hydrogens could you hold?
18. Well,
C8H10 would be fully saturated. Double it and add 2, right? When you take away 1 carbon from that and replace it with a nitrogen, what happens to the total number of hydrogens you can hold?
It changes because nitrogen only has 3.
Okay, we lose the ability to hold 1 when we go from C8 to C7N, so it can only hold 17. So that C7H17N is fully saturated.
Right.
Right, and that one makes sense for an answer for that problem.
So that one's probably just a change.